Okay. So this talk is about the quantum simulator deep dive. We have Dr. Guerreschi and Dr. Helena Liebelt giving the seminar. So please, you have the floor.
Thank you, Enrico, for the introduction. Can you see my screen and hear my voice? Okay, that's great. So first of all, thanks for having us. Thanks for the invite. Today, I'm gonna give all the full presentation. Helena is also here connected, and I'm gonna talk about Intel Quantum Simulator. A bit differently from some other talks from the industry players in which a roadmap is presented. Here, we wanted to give a bit more technical information about really how the quantum simulator works under the hood. Okay. So the presentation is divided in two parts. The first one is short, is substantially a quick introduction to quantum computation, just to mention a couple of concepts that we will use during the talk. And the second part, we will ask why we need a quantum simulator and try to clearly answer this question. The second part of the talk instead will be about the Intel Quantum Simulator itself. And so we will discuss a few aspects of how we represent the states, how it represents an operation on the states, and then a few other features that we would like to highlight. So, sorry, let me maybe start also count a time for the presentation so that I know how we are doing. Okay. Quantum computation. In a nutshell, quantum computation is a new way to store and manipulate information. And the hope is that having access to a different kind of operation that we call gates, we also brings to a different algorithms that has a different scalings compared to their classical counterparts. The hope is really that in the scaling behavior, quantum algorithms are faster than or requires less steps or computation than classical algorithms. Now, typically one can look at an operation acting on multiple qubits. But a nice property of quantum computation is that every of these operations can be decomposed into the action of a 1 and 2 qubit gates only. And in particular, this is just a point for the talk, a single kind of 2 qubit gates is sufficient to achieve universal quantum computation. So the scope then of the simulator will be to be able to prepare a state, so initialize the states, to apply 1 and 2 qubit operations and then measure the states and extract information. Now, how can one visualize quantum algorithms? Typically, they are shown on the left like a sequence of quantum assembly instructions or QASM instructions. Otherwise, on the right, they can be visualized as a quantum circuits. I think that I don't have to enter details on the explanations. Now, the question is, why do we need a quantum simulator? And there are at least two practical reasons why we want a quantum simulator. The first one is like we want to understand the performance of quantum algorithms. And in the early age of quantum computation, algorithms came with a sort of performance guarantee. Things in terms of a Grover search algorithm or the Shor algorithm for factorization. They provide an expected number of operations that are required before achieving solution. In the recent years, instead, things change a bit, and quantum heuristics algorithms are now entering kind of the field. And with these heuristics, we don't really know what is the quality of the solution that we achieve, and we don't really know the number of operations required to achieve such solution. So I think it's particularly important to have a simulator to kind of address the performance of these algorithms. The second point is that having a quantum simulator together with a realistic noise model will allow us to characterize the noise sources in the devices that we are building. And this characterization should go beyond just a qualitative understanding of the noise, but really move towards a more quantitative understanding. There is also a third reason that this is more for this high-performance community or high-performance computing community, that is really like the simulation of quantum systems is one of the tasks that very naturally extend to the exascale. So now that the exascale machines are coming up, then simulation of quantum system is one of the very natural applications. On the other side, you may have followed the news that about 1 year ago, Google claimed the achievement of quantum supremacy. So what does it mean, quantum supremacy? In a kind of also here in a nutshell, is that Google was able to perform on a quantum device a task that is impossible to perform under a reasonable, in a reasonable time in any possible classical system. This also means that the device that they had is not simulatable, right? Because if you could simulate, then you can also reproduce the same task. So are we in an era in which quantum devices are already beyond simulation? So is there still a values for the quantum simulator? And and yes, I believe that there is, and I tell you why. For both points, for me, are still very valid. The first point is that there is kind of a knob in a simulator that you can turn and decide what is the level of noise. And actually, for the approach that we are following, the simulation of an ideal system, so a noiseless system, actually takes the least amount of computational time. So that we can even think in terms of a simulator, just being able to simulate high quality qubits or even error corrected qubits, something that at the moment will require, from a physical device, a large overhead. From the second point of characterize the quantum devices, I believe that being able to simulate 30 or 40 qubits also with noise will help us a lot to understand long range errors or interaction between the qubits. And so I believe that both applications are here to stay. There is a small teaser that I want to add. If one look in the very long terms, how to characterize a quantum devices, when we want to characterize larger and larger modules of this device, we are proposing, together with some colleagues from Toronto and Harvard, a quantum computer aided design. So the idea that we could use a quantum computer and quantum algorithms to try help designing the new generation of quantum chips. But this is not the content of today's talk. The content of today's talk is really Interquantum Simulator. And Interquantum Simulator is being released open source. We changed the repository about 1 year ago, so I just want to remind the people the link. So not everybody has adjusted. So please, in case if you intend to use, just explore the repository. You can ask a question, you can develop even and contribute. So we are very open. Let me see, sorry, I'm just reducing my picture to read better. There are multiple features, some features that I think that came from moving from what felt like a research project a few years ago to what is really a more mature open source project. Part of this transition was clearly creating a more robust building process that doesn't require, really much of the understanding of how it works. It's based on CMake, it's customizable. We extended the tutorial, the examples, but there is also a Python binding. So the Interquantum Simulator also builds as a Python library. Now we see Python that is kind of dominating language into the quantum computing frameworks. So in this way, you can very easily use Quantum Simulator, Interquantum Simulator in Python. For example, we have multiple Jupyter Notebook as examples. The core, however, of Interquantum Simulator is really being able to leverage all the computational boost coming from high-performance computing environments. So it's a parallel and distributed implementation. And this implementation that will be the focus of the next part of the talk. So first of all, let me set a bit the stage. What do I have in mind when we speak about this high-performance computing environment? We consider a network of computing nodes, right? And in which every node has its own processing power, CPUs, but has also its own local memory. And there is a high bandwidth interconnections between the different nodes. The first part to understand the simulator is really thinking how the simulator represents quantum states inside of it. So a state of n qubits is typically represented as a vector of 2 to the n complex elements, okay, or complex amplitudes, how we call it. And this makes it clear that the memory cost grows exponentially. You just add 1 qubits and you double the space. You arrive at a certain point very quickly in a way that you exhaust the local memory available in your node. So how we are able to simulate more qubits? The idea is kind of simple. You just divide the states into different parts, and then you separate the parts and store each part of the state vector into different nodes or processor in this case. If we have 2 to the p processors, we will have that every local memory has size 2 to the m, when m is equal to the number of qubits n minus p. Now, why I'm stressing out this p, m, etc.? Because given n qubits and this configuration, we will say that the first m qubits are local and the remaining p qubits are global. What do we mean? We call substantially a local qubits a qubits for which, if we have to simulate a gate on these local qubits, we do not need communication in the simulator. Let's look at how it works. We have a state here. It's an example of a 3-qubit state. So it has 8 amplitudes from indexing from 0 to 7 in binary notation. And let's imagine that we have 2 processors. So we have 2 memory spaces, memory space 0 and 1. In this case, we have 3 qubits. 2 of them, the one of low index, will be local qubits, and 1 of them will be a global qubits. What does it mean, apply a 1-qubit operations? A 1-qubit operation can be seen as a 2 times 2 matrix. It's here visualized at the bottom. And then this matrix, if you want, you can apply a tensor product with identities to really creating it, representing as a matrix on the full states. But I think the idea is, like, if we apply this gate U on the qubit K, the amplitudes are actually updated in pair, okay, as is shown in the right side, in which we select 2 amplitudes that have the same index in binary notation apart from index K. The same, let's say, the bit K is the same as the index of the qubits we are acting upon. How do we visualize this action in amplitudes, right? I'm showing 3 different patterns of this amplitude pairing, coming from the application of a gate on qubit 0 on the left, on qubit 1 and qubit 2. What we can see is that for acting on the local qubit 0 and 1, these amplitudes that needs to be updated together are actually paired by this red dot line, and none of these lines cross the memory boundary. This means that the amplitudes can be updated without the need of communication. This is different from what happened for the global qubits, in which actually all these pairs are stored in different nodes. In this, to be able to perform the simulation, we then need communication. The kind of the reference provides is the first publication about interquantum simulator, and provide the communication pattern from MPI. Here we have also said that it is required to perform not only 1-qubit operations, but 2-qubit gates as well. And interquantum simulator allows the application of 2 kinds of gates. One is the control gate, so in addition to arbitrary 1-qubit gates. So you can apply control gates of the form on the top, or swap type gates that is of the form of the bottom. Either of the 2 is sufficient to achieve universal quantum computation, so we can simulate every circuit. But what is the beauty of this form of gates? If you kind of give a look at the matrix form, there is never more than 2 non-zero elements per row or column. And so this also means that the amplitudes, when we want to simulate this, are updated at most in pairs. And so we can use the same concept that we discussed for the 1-qubit case, and we obtain similar results about if you apply the gates on local qubits, you don't need communication. Quantum simulator, the interquantum simulator is a distributed code, right? And so one of the questions in high-performance computing is immediately try to address how well does it scale to more computing nodes. If I have, in particular here, I'm presenting the strong scaling study. The strong scaling is I fix the problem, and then I assign more and more classical resources to solve it. And the idea is like, how does the computational cost scale, right? The best hope scenario is like if I double the number of computational resources, the time will halve. So let's look at what exactly we are plotting here on the left. I don't know if you can see my mouse, but let's focus on the blue curve that is the one at the top. We are reporting the time that is taken to simulate a 1-qubit gate while we are swapping the qubit index, okay? You will see that at the beginning, the cost of applying these 1-qubit gates stay constant. This is what happened when we apply, when we want to simulate a gate on a local qubits. But if you see, in the last 5 qubits, we have to pay a high price. This is why there is this jump in the cost of the on the time of the simulation, because now the communication overheads kicks in. The blue line, in fact, has 32 processes. 32 is 2 to the 5, so the last 5 qubits are global. Now, this is not the scaling study, right? The scaling study is like, okay, now we have 64 processes, so the orange line, or we double again, we have 128 processes, the green line. And so how does the time scales? This is a log plot, and so you can really nicely say that every time we double the classical, the computational resources, we actually halve the computational time. So that's a very good behavior. The only caveats is that also more computational resources we have, more qubits will be global. And so the communication overhead start kicking in for smaller and smaller number of the qubit index. I am left about, I believe, like 6 minutes before the question kicks in. So I would like to discuss a couple of selected aspects of interquantum simulator. And I would like to start from what we call the pool of state functionality. That is something quite unique, I think, to interquantum simulator. So this is a functionality that the idea is like it will allow the simulation in parallel of multiple circuits. So let's look at the use cases. There is kind of these 3 plots, starting from the left. The left one is what we thought at the beginning as the original use case for interquantum simulator. We wanted to simulate as large of a state as possible. And so we wanted to chop the kind of the states into as many pieces as possible to fit in a local memory. And this is what is shown on the left, that all the processors and all their local memory is used to store and process a single quantum state, and so a single circuit. If we move towards the right, we can see actually that we can divide the processors into groups, and each group of processor can actually deal with a simulation of one and only one state or circuit. And if we move even further, we could go to the case in which we use a single processor to actually simulate multiple circuits. Now, clearly, going from left to right makes that the number of qubits per circuit is reduced. But we can enhance a lot of the parallelisms, and this is taken care inside the interquantum simulator itself. There are 2 use cases that we find very natural for this pool of states feature. The first one relates to the very famous now class of variational quantum algorithms, in which substantially we can dedicate each of the different instance or circuits to running one of the variational algorithms with a very specific selection of the parameters. The second use case is actually when we want to simulate noise and decoherence. This is what I would like to expand a bit more on. So if we simulate, interquantum simulator is a pure state simulator, right? So in general, it will not include noise. And we can see from on the left side of the slides, the pure state is a vector for n qubit as dimension 2 to the n. And the simulation will be substantially we are simulating a circuit here captured by the unitary U, that is a multi-qubit unitary. And we have a state at the beginning and a pure state at the end. What happens if we introduce noise? When we introduce noise, actually we need a different kind of object to store the quantum information that is called density matrix. And so the density matrix is now a 2 to the n times 2 to the n matrix that takes quadratically more memory than just a pure state. So quadratically more memory in terms of qubits means that with the same total memory available, we are able to store only half of the qubits. This is kind of a steep price to pay. But there is a way to go around it. So at the bottom, we can see exactly what will be the simulation. You start from a pure state, right? You start with something without noise. You apply, this is kind of a noisy version of the circuits, this kind of U, and you obtain a density matrix in output. But there is some theorem that relates the density matrix in output to a sort of average over multiple realization of perturbed version of the circuits U. What do I mean? I take my noiseless circuit U, and then I perturb it in a stochastic way by adding extra gates or by kind of mimicking the mistakes or the error that can happen. And this will give rise to these circuits UK. Now, UK is just an index to mean that is generated according to a certain distribution probability of perturbed circuits. Then I need to average over multiple realization of these perturbed circuits. And if I average over a large enough number of circuits, I will actually reproduce exactly the noisy case. So how do we use it? Once we reproduce the noisy density matrix, we can also compute expectation values of observable. That is typically what one cares about at the output of a quantum computation. So the question here is really how many perturbed states can we sum? And on the right side, we can show how does, let's say, the expectation values of an observable converge the more perturbed circuits we are averaging. On the top, it can be seen that if we average around 100 circuits, we actually converge in this case. But there are cases, like at the bottom, in which we have to average maybe thousands of circuits. Now, this is exactly when the pool of states helps. We can divide this 1,000, for example, perturbed circuits that we want to to average to obtain the noisy results over the different processors, right? And so we can perform them not sequentially, but in parallel. And so we can speed up the computation simply linearly in the number of classical resources available. Let me flash slides with a couple of more features of interquantum simulator that I want to highlight. One was the Python library, right? And we are releasing very soon a new kind of update in which we are actually also using MPI environment or MPI communication protocols inside Python, so that one will be able not only to use Jupyter Notebook, but really perform eventually simulation at scales, writing just Python code. Some other things that I want to mention is that we have a Docker file, so it can be built also in a container space for somebody who wants, to think more in terms of a container. But in this case, at the moment, there is no MPI protocol involved. So can interquantum simulator be useful to your research? If yes, please give a look to the repository. You can ask information. We are trying to be active in replying. Excuse us if we are not super fast, but there is a very great, let's say, motivation from our side. On the other side, if the simulator is not what you need for your research, maybe you can ask for adding the functionality that you need. Or even better, this is the beauty of an open source project. You can even think about developing them. And with this, there is the legal information slides. Clearly, what I talk about today is for educational purposes. Okay, nothing, not giving you any intellectual property. And then I would like to thank you all for listening to the talk, and thanks clearly to the team, to the interquantum simulator teams that helped develop the simulator, and to all the contributors in GitHub. Thanks a lot.
Thank you. Thank you for this very interesting talk. I do have a question, very technical. It's about the 2 qubits gates.
Yes.
So what kind of operations do you have in mind? Is that something implemented to emulate something which is going to be built at a physical layer, or is that something you consider prepared at the quantum error correction level as a logical qubit?
Yeah. Yes. So I would say that the distinction here is not okay. So on one side, it depends on the level of fine graining that you want for the error correcting qubits, right? I think that the application are twofold. One is really mimicking physical qubits, especially while we spoke about noise, etc. This will be a physical qubit level. When we want to speak instead and apply to, let's consider that one hipster qubit is a logical error-corrected qubits, we have to neglect then the error procedures, the error-correcting procedures. So we will not fine-grain into the specific error corrections, but we will just use the error rate that doesn't reflect the physical one, but the error-corrected one. So I would say that the most natural answer would be think more in terms of physical or abstract qubits. Yeah.
Okay.
Do you have to comment on the kind of 2 qubit gates, or?
Oh, it's okay.
Okay.
Yeah. So let me thank the speaker.